Okay, second video on the DHSS model. So, we've put ourselves back in the early to mid 70s. Economists, Solow, Stiglitz, Dasgupta, Heel, they've seen this limits to growth stuff, they don't believe it, they want to incorporate economic mechanisms. They've got the solid growth model with capital accumulation. They've got a cake eating model. They put them together. And of course, the cake is the natural resource, the non-renewable natural resource. It's an input to the production of the final good. So we combine the two models and it looks like this. Could this be our workhorse model? Well, we'll see what happens. So we want a model that will match stylized facts about global markets while having something interesting to say about the future. So thus far, global markets, how we know they worked for the last 50, 100 years, whatever, 200 years. What are the stylized facts about quantities of natural resources? What are the stylized facts about prices? Well, we're going to find out, I think. Yeah, we are. Oh, let me just check. Yeah. Okay. And let's compare to the model. And we're going to start with the very simple version of the model that was the sort of canonical version or the core version used by Dasgupta, Heel, Solow, Stiglitz, which was a model with no capital depreciation, no technological change, and no population growth. Okay. So let's see what happens. What are the stylized facts about prices and quantities? Let's have a look. So the cake eating setup leads to an immediate prediction about resource prices. Explain briefly. Does this fit the data? Okay, so this is basically hoteling. Okay, so how do we explain this? Basically, the cake is an asset, right? And if there's a discount rate and an interest rate in the economy as a whole, that means that if you're going to hold an asset, you want its value to appreciate at that rate. If it's appreciating more slowly than that, you want to shift it, get rid of it, and transfer it, buy some other asset which is appreciating at that rate. Okay. So evidently, if it's not appreciating fast enough, that means that its initial price must be too high. Okay, it's on the wrong path. It's a little bit like these paths, right? It must be sort of on the wrong path. And we need to drop onto the right path, which means that its price should drop instantaneously and then start rising at the right rate, because everyone wants to sell it. Okay, if its price is rising too fast, then everyone wants that asset. So everyone's like, oh wow, this asset price is rising super fast, let's buy this asset. Everyone wants to buy it, the price will jump up instantaneously, and again we start off not on the right path, we'll jump up to the right path. On the right path, the asset price has to grow at the interest rate. Okay, this is all with perfect markets, perfect information, and so on. Okay, and crucially, zero extraction costs, right? This is cake. Okay, so immediate prediction about resource prices. They should grow at the interest rate, which means they should grow pretty fast. Does this fit the data? Well, we'll see shortly. if resource prices are growing like that, what will we expect to happen to quantities? Plus, of course, we can go back to the cake eating model and say, look, the quantity clearly has to decline in the long run. It's conceivable there might be a hump early on if there's some kind of transition to a steady state or a balanced growth path, but in the long run we definitely expect to see something like this. And as we said about Solo, let me see, yeah, these transitions, they happen pretty quick, right? 20 years and you're on to the balanced growth. So we would expect to see resource price should rise at the interest rate, quantity you would expect to see declining. What do we see? So this is some data that I put together for my paper from 2016, and this is global product. This is the quantity in tons of all metals extracted from 1900 to 2018, I think. No, can't be 2018. Must be 2010 or 2012 or something. And this is a log scale. Okay, so a straight line here is a constant growth rate. So basically the quantity of materials extracted has been growing along with global growth in GDP. This is global quantities. Prices, real prices corrected for inflation, more or less no trend. Constant, if you like, but of course they are varying in the short run. Primary energy, same story. Okay, quantity of primary energy tracking global growth, price, no trend. Okay, admittedly with some quite big fluctuations here since the 70s, but in the very long run, no clear trend. Okay, so clearly these immediate predictions from the model aren't fitting what we see in the data. One way we could get rises in consumption in an economy without technological progress would be to assume that the economy is on a transition path with steeply rising capital. But that's actually hugely difficult to justify. Partly you have to explain how come the economy got into a position with way too little capital. Maybe there was a huge earthquake or something, but which destroyed all the capital. But otherwise you expect capital to keep pace with technology, capital growth. And these transitions, part of the reason for that is that we know from the Solo model and when we put parameters in and sort of choose reasonable functions and so on, that these transitions are very quick. And we also see that from historical data. Countries that have had their capital stocks destroyed by war or natural disasters, their GDP bounces back very quickly. For huge disaster for after a war or something, within 10, 15, 20 years, you've got your capital stock back, you're back on trend. So this transition path idea just doesn't stand up to scrutiny at all. Okay. So the model seems to lack empirical relevance for the present. Might it tell us interesting things about the future? That's what we're going to look at in the next video.